Okay, so nuclear chemistry. As one of my previous videos had said, right, it's all about the electrons, except for when it isn't. And this is when it isn't. So nuclear, right? The first thing that we're going to talk about is nuclear notation because it's a little bit different from the notation in other chemical reactions because it's going to include the numbers of some particles, right? So if you look over on the side here, we've got the mass number. Oh, I don't know why that's changing slides. The mass number right up at the top here, and then the atomic number on the bottom. And so as it says here, written right next to it, right, mass number on the top is the number of protons and neutrons. And then, of course, the atomic number, just the number of protons. And we need both of those because when you are looking at nuclear reactions, you're going to be dealing with a lot of isotopes, right? And if we remember what isotopes are, that they are atoms with a different number of neutrons, and that will give them a different mass, right? Like if we had carbon 14 here, right, this would be 14 instead of 12 if that was the isotope carbon 14 that we were dealing with. So that's why we put our mass number and our atomic number on here when we are doing nuclear reactions, because it's all about keeping track of where the nuclear particles are going. And so, nuclear particles, what are those, you might ask? Well, here's a list of 4 of the most important ones that we will see. There's 1 or 2 more that you won't really come across too often unless you become some sort of nuclear physicist. And at that time, you learn them then. So the 4 that we deal with most, alpha particles, these are basically a helium nucleus, right? A helium atom with all the electrons removed. And we can represent them one of 2 ways, right? 4,2 with an alpha, or 4,2 He, right? Helium. So those are the 2 ways we can represent that. Beta particles. These are pretty much just electrons. However, they are distinct from electrons in that we consider them to be ejected from the nucleus when certain nuclear changes occur. So they are listed as 0, having no mass number, and having -1 as their atomic number, or that they are a negative of a proton, and the symbol beta there. Okay, then neutrons, all right, they are neutral. They have no charge, right? So atomic number of 0 and a mass number of 1 because they just have a neutron. And then N for neutron. And then gamma, all right? This one, not a particle, but it is high energy electromagnetic radiation. So really high energy radiation. We say it has 0 and 0 for its atomic number and its mass number. And then this is the letter gamma from the Greek alphabet. So those are the 4 nuclear particles that we will deal with. And then there are also 4 types of nuclear reactions that we will look at: fission, fusion, nuclear decay, and transmutation. Fission, okay, this is the one that occurs in nuclear reactors here on Earth. And fission, this is when heavy nuclei, or nucleuses, or a heavy nucleus, is struck by a high energy neutron and splits into 2 or more smaller nuclei and more high energy neutrons. This can be naturally occurring, but it's most commonly found in nuclear reactors here on our planet. And so you'll notice here, one of the big things with nuclear reactions is that all of the stuff on this side, right, on top and on the bottom, has to be the same as all the stuff on this side, on the top and the bottom added together, right? So like over here, 0, 92, that's 92. 56, 36, and 3 times 0, that is also 92. And then 1 and 235, making 236 on the top. And here we've got 141 and 92, making 150 or 252. Boy, my math is I'm really having a tough time with math today. 233, and then 3 times 1 is another 3 for 236. So there we go, right? The same number of things on both sides, and that's what nuclear reactions are all about. Same number of protons and neutrons on both sides of the equation. Fusion. When 2 or more nuclei combine to form new, heavier nucleus, often naturally occurring. This is the process found in stars, and this is part of the formation of helium in a star from hydrogen. However, we've already gotten to the point where we have tritium, so we're not showing the entire nuclear reaction. But basically, you take 2 things, you smush them together, you make one new thing. And again, just like before, all the stuff has to add up. Okay, nuclear decay. So when an unstable atom releases nuclear particles to become another more stable element. So this is often naturally occurring, this process by which an unstable radioactive atoms become more stable. So when something is radioactive, it is going through this process of nuclear decay in order to become stable and or not radioactive. And so often, right, you will make some element and some various number of nuclear particles depending on whether it is alpha or beta decay, or there's a couple others, but mostly we'll see alpha or beta. And again, just like with everything else in nuclear, you have to have the same amount of stuff. The numbers have to add up to the same thing on both sides. And then the last one, transmutation. This is when an atom absorbs high energy nuclear particles to form a new element, usually heavier. This is often not naturally occurring, though this is the process used to create all the man-made elements, right? The last naturally occurring elements on Earth is number 92. So everything after uranium, right, number 92 on the periodic table, is man-made. It does not exist naturally in the universe as far as we know, though there is some speculation that all of those really heavy elements, because they are very radioactive, were made a long time ago when there was a lot more exploding and stuff going on out there, but that they have all since decayed to lighter elements. Okay, so now I know the question that you are all asking: how dangerous is radiation? So if you have alpha or beta rays, not terribly dangerous. Paper or something thin, such as aluminum foil, can block both alpha and beta rays, right? So if you're wearing your tinfoil hat, you're safe from those beta rays. However, gamma rays and X-rays, those are a little tougher to block. You need something like lead, which is why, you know, when you go to the dentist and get your teeth X-rayed, they put on that lead vest. And then if we're talking about neutrons, right, like in a nuclear reactor, that is really tough to block. So you need a lot of water or thick concrete to stop neutrons, which is why nuclear reactors have both what's called heavy water in them and are lined, the reaction chambers are built out of like 10-foot thick concrete walls so that they can stop all of those neutrons from escaping, and all that reactivity and dangerous neutron rays do not come out of the nuclear reactor. Half-life. Okay, we are definitely going to do some calculations with half-life. I'm going to present the equations here, and we will work with them in class instead of taking time right now to go through an example. I will give an example in class. We can write it down there. What half-life is? It's the time it takes for half of a given amount of radioactive material to decay. All right, so basically decay to 50%. That is the half-life. So this depends on the stability of a radioactive isotope and can vary greatly from a tiny fraction of a second to many trillions of years. Right? So it is very, very varied in how long it is. So the equation, N sub T equals N sub O times e to the negative kt, and with k equal to 0.693 over t to the sub 1/2. Now, if you don't know what all those are, I have a list right here. N sub 0, that is your starting amount. N sub t is the ending amount. T sub 1/2, of course, the half-life. K is the nuclear decay constant, and T is time. For those who don't know about E, E is a constant as well. It is a number. I don't remember the value of it off the top of my head, though I probably should at this point. It's like 2.3 something. You can ask your math teachers all about E. I'm sure they would love to tell you about E, which is also the number that for natural log, right? Natural log is log base E instead of like log, which is log base 10. So all of this works together. Basically, you have your starting amount. It is multiplied by e to the decay constant multiplied by the time that you were talking about, how long something has been decaying, and all that together will give you the amount that you have remaining after time t. So we will work with this in class. Don't worry, write this down, write down what all this stuff means, and we will take a look and practice some half-life. Okay, nuclear stability. So Z, right? Effective nuclear charge. Look at that. We're talking about that again. Or protons and neutrons. We're not talking about effective nuclear charge again. Protons and neutrons. So you can see down here, right, where you have the protons and neutrons, it starts out where you have a 1-to-1 ratio of protons to neutrons in your nucleus of an atom, right? And so this is, right, if this is protons, this is also atomic number. All right, so right up until about atomic number 20, you have a 1-to-1 ratio of protons to neutrons in the nucleus. However, it then starts taking this steep upward slope where the nucleus is no longer stable at a 1-to-1 ratio, right? All this stuff in the middle, you start needing more protons, right? N, more protons for every neutron, or sorry, let me start again. As you get here, after about 20, you start needing more neutrons for every proton in there. And so if we think about this, it makes sense because protons, they're all positive. They don't really want to be stuck together in that tiny space of the nucleus. And so what's going to happen is you're going to need more neutral stuff in there to kind of buffer all of those protons so they don't just shoot away from each other and have your nucleus explode. However, if you look up here, right, because it says black dots are stable, if you look up here, suddenly there's nothing stable after about number 80, right? So number 80, can't remember exactly what element that is, but somewhere around radon, right? Everything after that is radioactive, right? There is no stable combination of protons and neutrons at that point. All right, everything after that is radioactive because you can't pile enough neutrons in there to keep those protons happy. So after about number 80, everything is radioactive. Nuclear reactors. How do they work? It's a good question. So nuclear reactors, there's a couple types of them. There's one main type that we use in this country that deals with pressurized water and using it to spin turbines. The main job of the reactor here is to house and control nuclear fission, right? Breaking nuclear particles apart. Reactors use uranium for nuclear fuel. The uranium is processed into small pellets and stacked together in metal tubes. Typically, more than 200 of these rods are bundled together to form a fuel assembly. A reactor core is typically made up of a couple hundred assemblies. So lots and lots of little ceramic uranium pellets. Inside the reactor, the fuel rods are immersed in water, which acts as both coolant and a moderator, right? Which means it helps to slow down the neutrons that are created by the fission. And so to sustain a chain reaction without letting it get carried away. Control rods can be inserted into the reactor core to reduce the reaction rate or soak up those neutrons so that it slows down the rate of the chain reaction. And the heat created by the fission turns water into steam, and it spins a turbine to produce basically carbon-free electricity because you're just heating and cooling water and spinning a turbine. So what is a chain reaction? Well, if you remember from the fission reaction that we looked at earlier in the video, a neutron strikes a large nucleus, that splits apart, releases more neutrons, those then hit more nuclei, split those release more neutrons, so on and so on. It is a chain and it just keeps going. That is a chain reaction. This is a diagram of a nuclear reactor. You can see where you're generating steam, you've got the reactor under pressure, you've got your condensers, your pumps, your turbines, your cooling towers, all of that. You can pause the video and take a look. A pressurized water reactor. This is the most common type, at least in the US, at this point. Okay, so Cherenkov radiation. This is just cool stuff. I just added this in because I thought it's cool. So the blue glow that you see in the pictures of these nuclear reactors, it's a real thing. These are not doctored images. These are actually glowing blue. So why does it glow like that? So this happens when a particle traveling through a medium, right, water in this case, is traveling faster than the speed of light in that medium. So remember, right, speed of light, basically 3 times 10 to the 8th meters per second, that is in a vacuum, right? Light travels at different speeds in different mediums. So in this case, right, water, light travels slower in water than it does in a vacuum. However, these particles are traveling through water faster than the speed of light, and it creates a wave that follows the particle, similar to a sonic boom when an object is moving faster than the speed of sound in air. All right, so it's a similar principle. It's just in this case, it's particles traveling faster than light rather than, say, a plane traveling faster than the speed of sound. Okay, the wrap up here. Nuclear reactions, they deal with the particles of the nucleus, not the electrons. Nuclear reactions almost always change the identity of the elements involved, whereas chemical reactions almost never change the identity of the elements. Radioactivity is the process where unstable nucleus becomes more stable, and all nuclear reactions release nuclear particles and energy, though not all of it is overly dangerous. As it says here, right, as I reminded you earlier, just wear your tinfoil hat. It'll keep you safe from those mind-controlling beta rays. I will see you all in class.